The first thing I need to do in this example is to determine the minimum number of unknowns that's necessary to analyze this circuit for mesh analysis. I can do that by redrawing the circuit and killing the sources. When I kill the sources, I replace the voltage sources with short circuits, and I replace the current sources with open circuits. So the voltage source V1 becomes a short circuit. The resistances R1 and R2 aren't affected. The voltage source V2 also becomes a short circuit. The resistance R3 isn't affected. And the current source, I sub S, becomes an open circuit. Now I identify remaining enclosed non-overlapping areas. So this area is enclosed. This area is also enclosed, and no part of it overlaps the first area. This area over here is not enclosed. It contains this gap. So we have two enclosed non-overlapping areas. The number of unknowns in the circuit is just equal to the number of enclosed non-overlapping areas. So in this circuit, the number of unknowns will just be 2. Next, let's take a look at a couple of different ways to define unknowns for this circuit. We've already determined that this will be an enclosed area once I kill the voltage source, and this will also be an enclosed area once I kill the voltage sources. So the mesh currents, our unknowns, go around the perimeters of these areas. So I'll have a mesh current that goes around this loop and a mesh current that goes around this loop. I'll arbitrarily call this one I1 and this one I2. Now when I use this approach, none of the mesh currents will go through current sources. I need to account for the current source currents separately. I'll do that with what are called constrained loops. So I know, for example, that there is a known current, I sub S, going through this current source in this assumed positive direction. I need to account for that current. So I'll create a constrained current loop that accounts for that current. The only rule for that constrained loop is that it has to match the magnitude and direction of the current through the current source. Since that's the only rule there are generally a variety of choices you can make for the constrained loop. For this particular example, I'll say the constrained loop goes through this section. It's got a current I sub S. It's got the right magnitude and direction to account for this current source. To emphasize that the constrained loops are somewhat arbitrary, let's do this problem a slightly different way. My mesh loops are more or less unique if you use the approach that I'm presenting here. So this is going to be a mesh current. I called that I1. There's no reason to change that variable name, and this is I2. The constrained loops can go anywhere as long as they account for all of the currents in the current sources. So my only rule is that my constrained loop has to go this direction through that source. I can create a constrained loop that goes all the way around here. As long as it's got a current I sub S, it's perfectly fine. I could also define a constrained loop that goes through this lower area. It goes in this direction through this current source, and it's got the same magnitude as the current source does. It's a valid choice.